Just a small suggestion. The way the camera is set up, it can see your computer. If you tilt it, yeah, just tilt it a bit more. I'll tell you exactly when it's not. So at that point, I can't see anything on it anymore. Just in case, your privacy. Welcome, everyone. I hope everyone enjoyed your break and finished your first assignment due 10 minutes ago. I just checked on my phone just a second before class started, and there was 348 submissions, which is great, except there's 377 people in the class. So if you're one of the 29 that didn't submit, you're late. So get it in. Yeah, I hope everyone had a great reading break, short as it was, 2 days. Plus you had some chemistry to be doing during that time if you didn't do it earlier than that. If you remember where we were at this time last class, we were partway through the unit on air pollution. And we are going to pick up where we left off today. We spent last class basically going over some of the important features, chemically speaking, about gases. We talked about units. We talked about states of matter. We talked about layers in the atmosphere and all this kind of stuff. There have been a few accompanying Instagram questions over the last week or so. So if you're not on the Instagram, if you're not on the account, if you're not following, and you want to get those questions, please do that. There's a bit of an echo, is there? Let me see if I can fix my sound. What if I do this and this? All right, people online, you'll have to tell me if this sound, is this any better? I sound like a robot, do I? It's always been my dream. Just tell me if it's a little bit better, and if not, I can try one more thing, and then I'll abandon it if it's not. Okay, very low. How about this? I'm eventually going to get this figured out. Really quiet. That's good. I think I fixed the quiet part. Problem is with the online, there's a lag, 10 seconds or so. Is it still really quiet? Or is it better? I can hear you, but there's still an echo. Okay, what if we go with this? Next try. Is this better audio? I don't know why my mic doesn't want to behave today. But we can get rid of it. People are saying same. Okay. Let's see if that last fix. Still echoing. Okay. One more thing I can try to get rid of the echo. Sorry to be doing this on the fly. How about that? Is that better? Or is it still a little robotic sounding? People say they can deal with it. Hopefully that sounds okay. There we go. Well, there was a 2 or 3 minutes of class well spent. Okay. So what we're going to be doing today then is picking up where we left off. And where we left off, if you remember, was talking about specific air pollutants that can be found in our atmosphere, in the air that we breathe every day. There's all kinds of potentially toxic things that could be present in our air that we have to be aware of and careful of. But what we're going to be focusing on in this class is the ones that are regulated by Environment Canada. These are the ones that are generally present in greatest amount, most common, and the ones that are really highest concern. We can still understand you all good. Okay, it's just audio quality, which I don't know what the problem is. It's not the mic. At least that wasn't money badly spent.
All right, so what we're going to be doing is looking at the additional gases that's in the air that we're breathing, in addition to the top 4 that we know are there, we need to be there. You know, there's nitrogen, oxygen, argon, and carbon dioxide. These pollutants, these next set of things that are much... I'm sure I don't have 2 mics on. Yes, I'm sure I don't have 2 mics on. I know how that can sound. Don't know what to do with the mic. You guys have to deal with it for one day. I bet you if I restart my computer, it would fix it, but I'm not going to do that right now. So yeah, I'm going to have to deal with it. The 6 pollutants that we're going to be looking at in more detail that are regulated by Environment Canada are carbon monoxide, nitrogen dioxide, sulfur dioxide, ozone, particulate matter, and VOCs. We're going to do them one at a time, and hopefully not spend too much time discussing each one. So the first one is going to be carbon monoxide. Carbon monoxide is a chemical compound made up of 2 atoms, 1 atom of carbon, 1 atom of oxygen, come together to form a molecule of CO. And where we get CO from, carbon monoxide, is typically when you burn any carbon-containing fuel, like gasoline, or charcoal, or wood, or anything like that, when you don't have enough oxygen to fully combust it all the way to carbon dioxide, CO2. So if you have a wood stove at home, often wood stoves will have a little like air intake valve that you can kind of slide open and slide closed. You slide it all the way open, you get lots of air go in, and just lots of the fire will burn faster. If you kind of cut it back and you cut the oxygen back, what will happen is your flames will get weaker. There's not as much air going in. What you're likely to get in that scenario is what we call incomplete combustion. Not enough oxygen to completely fuel the flames, and then what you're going to more likely get is some carbon monoxide. So this is just looking at a chemical reaction between a molecule of carbon, which is what you would find in a piece of coal or charcoal, and a molecule, this would be like C plus O2, which is a molecule of oxygen with 2 atoms of oxygen, making 1 molecule of CO2. So this would be called complete combustion because we've burned carbon all the way to form CO2, which is the most oxidized carbon can become. This is a balanced reaction because you have the same number of atoms on each side of the arrow. I talked about that before too. Whenever we balance an equation, you always have to make sure you have the same number of atoms on the left side and on the right side of the reaction arrow. You can't have atoms disappear, and you can't have atoms appear out of nowhere. And this goes back to that law by Lavoisier, which was law of conservation of mass. Right? We talked about that a couple of classes ago. All right, so this is a balanced equation, but if you try to do the same equation in an environment that does not have enough oxygen, what you're more likely to get instead is not CO2, but CO, which is obviously not fully oxidized. It can still take another oxygen. Not just carbon, but natural gas, which is methane, which I don't think anyone around here probably burns to heat their homes, but in different parts of the country, that's certainly an important fuel source. This would be the balanced equation, or not the balanced equation, the unbalanced equation to show that combustion. You have CH4, which is methane gas, reacting with oxygen to make CO2 and water. Problem is, the reason why this isn't balanced is this has 4 hydrogens on this side, but only 2 hydrogens on that side. So what we have to do if we want to have a balanced equation is we put these numbers in front. We call these coefficients. And what that means in this bottom example is that 1 methane will react with 2 oxygens to make 1 molecule of CO2 plus 2 molecules of water. And if you count up the atoms, if you count up the carbons on the left, there's just 1. Hydrogens, there's 4. Oxygens, there's also 4, because there's 2 molecules of oxygen 2 atoms per molecule, total of 4. So you have to have the same totals on the right. C equals 1, H equals 2 times 2 is 4, and oxygen equals 2 for the CO2, plus 2 times 1 is 4 as well. So you have a balanced equation when you have the left side and the right side of the equation with the same number and same types of atoms. Great. So in your car, you burn gasoline. Gasoline is a complex mixture of a lot of different chemical compounds. You go to different gas stations, that mixture is going to be slightly different. But one of the important molecules in there is octane. And in fact, gas quality is sometimes measured in terms of its octane number. And the balanced equation for the combustion of octane in your engine is the following. 2 molecules of octane react with 25 molecules of oxygen, give you 18 waters, 16 CO2s. Now this is under ideal conditions. This is the reaction you want to be taking place inside your engine when you start your car and start out your driveway down the street. This is completely combusting the gasoline to CO2. We know CO2 isn't necessarily the best thing to be putting out into the atmosphere in terms of global warming, but at least in terms of toxicity is very low. These gases are fairly innocuous, at least at the local level. However, if your car is not functioning properly, if you're not getting the right mixture of gas and air, and in fact, cars typically today have oxygen sensors that try to get the perfect mix of air and gasoline in your engine so that you get the top reaction, not the bottom reaction. If that's malfunctioning, if that light is on your dashboard, you haven't got it checked out yet, you may have a bad mix of gasoline and oxygen, and if there's not enough air, not enough oxygen in there, this is the reaction you're likely to take. This is the balanced equation on the bottom here for the incomplete combustion of octane that could take place in your car. And it's making carbon monoxide instead of carbon dioxide, and hypothetically, that could go out the back of your car, out of the tailpipe, into the general environment, and if it's an enclosed space, that's very dangerous. If it's out in the open, if there's enough cars, it can be dangerous for people just walking on the side of the street as well, or you breathing in air from your surroundings. Okay, so we got a question here on balancing. It says, in order to balance the following equation, what number must go in the blank? And here we have, basically what you do is you count up the atoms on each side. So on the left, we don't know how many sodiums, whatever number we put in front is how many we're supposed to have. Hydrogens, we have 2 times 2 is 4. Oxygens, we have 2. On the right-hand side, you can see there's going to be 2 sodiums because we have 2 times NaOH. Hydrogen, we have 1, 2, and then 3 and 4 because we have 2 NaOHs. Oxygen, we have 2. So that means the number that needs to go in front of sodium is going to be 2. Cool. All right, so modern cars, carbon monoxide, I guess I'll say this, used to be a much bigger issue than it is today. And there's been 2 inventions in cars since the 1970s that have really dramatically reduced the amount of carbon monoxide that modern cars will emit. One of these is oxygen sensors, okay, which makes sure that you get a good mixture of fuel and gas to minimize the production of incomplete combustion, minimize the production of carbon monoxide. The other important one is a catalytic converter. And this is part of your exhaust system. And I just was reading the other day, these contain metals like platinum or rhodium that are very expensive metals, relatively rare, and they're worth quite a bit for the metals themselves. And I was reading an article the other day about Priuses. Toyota Priuses have catalytic converters that contain a lot more of these metals than most other car makes. And the reason is they have emission standards which are better than most other cars. And one way they meet these standards is to have a higher quality catalytic converter. And for that reason, people apparently target these vehicles and they jack the car up, climb underneath, and cut the catalytic converter out of the car. Because it's just sitting kind of exposed on the bottom of the car. So if you own a Prius, and if you're in an area where this is likely to be an issue, actually there's companies that sell basically cages that you mount on the bottom of your car, which, you know, if you knew what you were doing, you could get them off. But it cuts down that sort of immediate crime of convenience, which who knew that this would ever be a thing you'd have to worry about with your car. Sure, someone might break your window and steal a wallet or something like that out of your car, but to climb underneath your car and cut out your catalytic converter, and I guess they do it for the metals, precious metals, platinum and rhodium. But what these do is they catalyze this reaction that you see here below. Takes carbon monoxide, combines it with oxygen, and makes it into CO2. So it sort of neutralizes the carbon monoxide as soon as it leaves your engine before it can go out into the wider environment. So catalytic converters, very, very important. Here's a picture of the catalytic converter on the bottom piece of the car. The worry with carbon monoxide is that it's actually extremely toxic to human beings. And we can't sense it in our environment. It has no smell. It's not visible. It's just a clear gas. If it's in our air right now, we could all be breathing it right now. We wouldn't even know. The problem is that CO has this structure, which is very similar in size and shape to O2. So when we breathe in air that contains carbon monoxide, it is the perfect shape for it to fit in to hemoglobin, which is our molecules that carry around oxygen. It fits in the active side of those and takes the place of where oxygen should be. The problem is that the enzyme is designed so that oxygen can go in and out easy. It can pick it up, transport it, and then release it where it's needed. Problem is with carbon monoxide, once it sticks to that enzyme, it doesn't come back off. So essentially, breathing in carbon monoxide is destroying your hemoglobin's ability to transport oxygen throughout your body. So it's basically causing you to suffocate even though you're breathing normally, and you don't even really notice. And what would happen if you breathed in too much of this in a short period of time is your body would just sort of slowly start to shut down, you'd get sleepy, you'd fall asleep, and you'd be dead. In fact, it was once a somewhat popular form of, not to say popular, but it was a common form of suicide where people would run their car engine in an enclosed space like a garage and just sit in the car. The idea is that carbon monoxide is being put out by the car, builds up in the atmosphere, you go to sleep, and that's that. I think with modern cars and catalytic converters and so on, that's going to be a more challenging way to do it. Although, it is still definitely a concern. And I've already seen it, right now, there's unseasonably cold weather happening in Texas. And most homes in Texas are not equipped to deal with cold weather. They don't necessarily have heaters, or furnaces, or insulation, or all these things that we kind of take for granted up here because we have winter. And what's happening are people are trying to find ways of staying warm without the proper equipment, and they're resorting to, like burning things in their house, or all these sorts of things that basically creating heat, but in a way that's jacking up the amount of carbon monoxide. And people are already dying as a result of this, which can definitely happen. This, by the way, is a pretty picture of hemoglobin that's in your blood, and that whole big structure is devoted to carrying 4 oxygens. So you can fit 4 O2 in this great big structure down there. Each one of these, by the way, this is an atom. That's an atom. They're all little atoms down there. So very, very large molecule to transport something very, very small. So really, carbon monoxide is a potential danger kind of anywhere in your home. Probably the most common thing would be like if you run out of power and people run a generator. That's fine as long as the generator is outside. If the generator is in the house, it can be putting carbon monoxide out into your house. Things like generators and lawnmowers and other gas-powered devices typically don't have catalytic converters. They're not cars, so they'll produce a lot more carbon monoxide than a car will. So really anywhere in your house where there's a source of combustion, it could potentially be a source of carbon monoxide and a potential danger. So this is just one example of carbon monoxide poisoning in CBC. This was in Newfoundland back in 2014, so quite a while ago. But again, when people lose power, they try to find ways like run a generator that can generate CO and pose potential danger. All right, so right now I have a ghost story for you. Okay, I'm gonna amp up the drama here a little bit. See if I can get this to work better. A little scarier, maybe. All right, perfect. I'm gonna get rid of that. I'm not holding that up for. All right, so we got a story. This is about a haunted house. And if you are Netflix fans and you have seen, what is it, The Haunting of Hill House? Something like that. I probably said it wrong. And there's also the other one, The Haunting of Bly Manor, I think is the... I watched like the odd episode of each of those series. I haven't seen the full series either way through.
I'm having trouble hearing you.
Oh, wait. I got a new Apple Watch, so I haven't figured it quite out yet, but anyway. I'll put it in my back pocket so it stops talking to me. Okay, ghost story time. This is a true story, by the way. True story. Unlike what you see on TV. All right, so this is a first-person account of a haunted house from a person who had lived in the house. And she says her husband, G, Mr. H, and I had not been in the house more than a couple of days when we felt very depressed. The house was overpoweringly quiet. The servants walked about on thickly carpeted floors so quietly that I could not even hear them at their work. One morning I heard footsteps in the room over my head. I hurried up the stairs. To my surprise, the room was empty. I passed into the next room and then into all the rooms on that floor and then on to the floor above to find that I was the only person in that part of the house. I had not been in the house more than a couple of weeks when I began to have severe headaches and to feel weak and tired. I took iron pills 3 times a day and spent a couple of hours each afternoon in my room lying down and resting, a rather discouraging process, as after resting my headache was always worse than it had been before. On one occasion in the middle of the morning, as I passed from the drawing room into the dining room, I was surprised to see at the further end of the dining room, coming towards me, a strange woman, dark-haired and dressed in black. As I walked steadily on into the dining room to meet her, she disappeared, and in her place I saw a reflection of myself in the mirror dressed in a light silk waist. I laughed at myself and wondered how the lights and mirrors could have played me such a trick. This happened 3 different times, always with the same surprise to me and the same relief when the vision turned into myself. As I was dressing for breakfast one morning, B, which is her son, 4 years old, came into my room and asked me why I had called him. I told him that I had not called him, that I had not been in his room. With big and startled eyes, he said, "Who was it then who called me? Who made that pounding noise?" I told him it was undoubtedly the wind rattling his window. "No," he said, "it was not that. It was somebody that called me. Who was it?" And so on he talked, insisting that he had been called and for me to explain who it had been. Some nights, after I had been in bed for a while, I have felt as if the bedclothes were jerked off me, and I have felt also as if I had been struck on the shoulder. One night I woke up and saw sitting at the foot of my bed a man and a woman. The woman was young, dark, and slight, and wore a large pitcher hat. The man was older, smooth-shaven, and a little bald. I was paralyzed and could not move when suddenly I felt a tap on my shoulder and was able to sit up. And the man and the woman faded away. Sometimes after I have gone to bed, the noises from the storeroom are tremendous. It does not happen every night. Perhaps a week or 10 days will pass, and then maybe several nights in succession. Sometimes it sounds as if furniture was being piled against the door, as if china was being moved about, and occasionally a long and fearful sai, or whale. We can take a break from the story for a sec and just comment that this is probably typical of most haunted houses, most haunted housing, I don't know how to say that right. Stories about haunted houses. There, that's how I'm going to say it. Where people see ghosts, right, which are described here as human people, humanoids that fade out or fade in, not really completely solid. They hear noises, wails, china moving, chains moving, this sort of thing, visions, all these sorts of things. And these experiences were actually pretty common. You don't hear about them too much anymore, but certainly in like Victorian times in England, these were very, very common, and a lot of people might have reported being in houses like this. And what people would say is if people who didn't experience this ever before visited the house and spent a few nights in the house, they would experience the same things. And if the people who lived there left and went somewhere else, they wouldn't experience them in the new place. So people all assumed the house was haunted because all of these observations are associated with the house itself and not mental health of the person living there or something along those lines. Saturday morning, the 18th of January, G's brother told us that he thought we were all being poisoned. That several years before, he had read an article which told how a whole family had been poisoned by gas and had the most curious delusions and experiences. He advised us to see Professor S. at once. He was out of town. His assistant, Mr. S., came to our house. We told him how listless and ill the children appeared. We found one of them lying on the floor and the two others in bed. We related the experiences of the children and servants and told them about the plants. So I skipped a few parts of the story too. He examined the house thoroughly from top to bottom and interviewed the servants. He found the furnace in a very bad condition. The combustion being imperfect, the fumes, instead of going up the chimney, were pouring gases of carbon monoxide into our rooms. He advised us not to let the children sleep in the house another night. If they did, he said, we might find, in the morning, some of them would never wake again. So here I'm going to go and ruin a bunch of fictional stories for you with some science. It's actually believed that most stories of haunted houses are describing real experiences that people experienced while in those houses, but it wasn't for supernatural forces, ghosts living there. It was because there was carbon monoxide building up in those houses. All of the symptoms of low-level carbon monoxide poisoning, when I say low level, what I mean is sublethal, doses that aren't going to kill you. Those are all associated with the symptoms, with the common experiences of people who report being in haunted houses. It makes sense that this peaked during Victorian times because at that time people would often be heating their houses with coal or wood or something like that. They would often use torches or lamps, lanterns, which had a flame in order to light the houses. And there were many combustion sources in the house and a generally poor level of quality when it came to ventilation or, like they didn't have wet certification then for installing chimneys and all this kind of stuff that we have today. The safety standards that we have today with anything involving a furnace or a wood stove today, far, far, far greater than they ever would have been at the time. So it would make sense that haunted house stories aren't really common anymore. And if you ever do hear them, it's always associated with old houses. You never hear a haunted house brand new construction. And it's because it's much more likely that an old house is still going to have old ventilation, old furnaces, and so on, which could be causing this problem to begin with. So there we go. We're not going to ruin all this for you, but if you're in a house and you think the house is haunted, check out the ventilation. Open some windows, get the furnace looked at, or the fireplace, or whatever it is that you're using to heat the house, and stay safe, because it's probably not ghosts. We're ruining a lot in this course, aren't we? That's what this course should really be about, is ruining fantasy. Because, whenever you're watching these shows now, it's just like go get your furnace checked. Like, quick solution to all these things. Because magic, right? Like Harry Potter style magic, wizards and witches and all that is like alchemy, just like a, you know, a little bit more fantastical version of alchemy as well. All right, this question should be dead easy. What toxic gas is produced by the incomplete combustion of hydrocarbons? Select one. SO2, NO2, CO, CO2. CO. Next. All right, next gas we're going to talk about is SO2. This is one atom of sulfur, two atoms of oxygen. It basically is formed anytime that you burn something that contains sulfur. So sulfur can be present in small amounts in things like wood, very small amounts, but it can be certainly present in much larger amounts in things like coal. It's generally not found too much in natural gas or gasoline. It's actually found in large amounts in naturally occurring natural gas. And when natural gas comes out of the ground, it's often called sour gas because it contains sulfur compounds. But before that goes into your home to be burnt, it gets refined. My uncle actually is an engineer that works at a natural gas refinery in Cochrane. And so they had to remove the sulfur. But coal, you can't easily remove the sulfur. And the amount of sulfur that's present in coal is characteristic of where the coal was mined. So coal from Cape Breton actually has higher amounts of sulfur than coal from some other places, like I think Virginia. And the amount of sulfur is going to dictate the amount of SO2 that's formed when you burn that coal. So what happens is you have sulfur in some form present in the fuel you're burning. It combusts, reacts with oxygen to form SO2, and goes into the air as a gas. SO2 itself is not the main concern. The main concern is when sulfur, SO2, gets into the atmosphere, it can further react with oxygen in the air to make SO3. SO3 will react with water in the air to make H2SO4. You know what H2SO4 is? It's also known as sulfuric acid. So there's a rhyme to remember H2SO4. It's little Johnny took a drink, but he will drink no more. For what he thought was H2O was H2SO4. There you go. So H2SO4 is a very strong acid. It's sometimes sold as a drain cleaner. If you have really stubborn clogged drains, you can run concentrated sulfuric acid down there and unclog it. The main problem with SO2 in the atmosphere, though, forming H2SO4, is that it'll collect in raindrops and come back down, and it'll create what's called acid rain. And if you look at Nova Scotia, much of our electricity in Nova Scotia is generated by burning coal. That number gets a little smaller each year. I think still, though, it's probably around 50% of our electricity comes from burning coal. And this is just one of the coal-fired power plants in the province. You might go to the city, recognize those two stacks. And you can see all that gas coming out the top. That's largely water, but there's probably a bit of SO2 in there as well. So SO2 is emitted, it comes back down, and acid rain, I'll say this, was a really important environmental problem back in the 1980s and 1990s, particularly in the Annapolis Valley, particularly in Nova Scotia, and other parts of the country. Why particularly here? A lot of the SO2 that is generated was generated by industry in the US, along the eastern seaboard. A lot of that air would move up across Nova Scotia, and it would come down as acid rain. So we got a lot of acid rain in Nova Scotia that we didn't produce. It was secondhand acid rain that was produced in the eastern US. And what that did is it fell. The acid rain caused ocean levels, lakes and rivers to become more acidic. And that actually reduced salmon populations in Nova Scotia by over 90%. What it also does is it'll strip nutrients out of soil. It'll cause soils to become more poor. It can stress plants. It can cause stands of trees to die. And this all depends with the amount and how severe it is, but it was definitely a big environmental problem and an increasing environmental problem as people were generating more and more electricity by burning coal. The map here of the U.S. is showing the emissions in 1995, with the red areas being the areas of high production. But only 10 years later, look at the map below, how much the SO2 emissions have been reduced. So when I say this used to be a big environmental problem, it's a large-scale environmental problem that we managed to fix, which we're going to look at a few of these in the course. And I hope these give you guys some hope because, we're facing other global-scale environmental problems now with things like plastics, things like global warming. And they may seem like such huge problems that they're almost insurmountable, but we've had huge problems before that we've been able to fix. And I'll say this, pretty well every example that I've seen of a wide-scale environmental problem that has been solved has sort of gone through three distinct phases. The first phase is purely scientific. It's basically scientists describing the problem, the scope of the problem, the extent of the problem, and the cause of the problem. Once that is sort of established, the second part is developing a solution to that problem, which might be a technological solution, might be a substitute for whatever was causing the problem in the first place, something along those lines. And the third part, which is the critical part, is political motivation, political will to actually force companies to use the solution, the alternative solution. So I feel like where we are right now is a very interesting time with global warming, for example, because we're past the first stage. We've identified the problem. We know what's causing it. We have a pretty good idea what the extent and scale is. We have lots of very good predictive models. The second phase of that problem is solutions. And there's all sorts of solutions that are currently being developed. A big one right now is solar energy, which has dropped in price by 90% over the last decade and is competitive with many other energy forms. Electric cars, another example. And these are really developing at a fast rate. The third one is the political will to force companies or people or whatever to adopt the less polluting or the more environmentally safe alternatives. Which, I think we're in the early stages of that. We have the Paris Agreement, which is, there's been many other agreements before it. We've had small-scale things like incentives, maybe to buy an electric car. You save a bit of money if you buy a car that way. Things along these lines. Taxes, carbon taxes would be another way to do this, but it's certainly, seeming to go slowly. But SO2 fixed in North America. This is another map showing the same thing from 1990 to 2010, a 20-year span. Dramatic decreases in the amount of SO2 released. And you can see there that this is just a table showing SO2 released up to 2010. So it continued to drop since 2010, in part due to the Clean Air Act in the US and in similar laws in Canada as well. SO2 in the UK, it's dropped similarly, same story along much of Europe. And the way they did this was by adopting a technological solution. And the technological solution to get rid of SO2, to get rid of acid rain, was something called scrubbers. And these scrubbers are devices that you put in line with the flue gas coming out of a coal-fired power plant, where the gas has to go through the scrubber before it can be released into the atmosphere. What the scrubber basically is the big tank like you see here. You can see where the flue gas is entering. It comes in sort of this side port here. At the bottom, you basically have this sort of lagoon of liquid where there's oxidizing gas being bubbled in. That's like oxygen or air being bubbled in under there. And then there's these sort of showers up top, these mist showers that are spraying this liquid mist that's down in the bottom here up and then back down. And what this mist contains is dissolved calcium hydroxide, which is also called lime. It's cheap and abundant, can be mined. It can be reacted with SO2. It does react in the air to produce CaSO3. It drops back here and the spray comes back down. And it's oxidized by the oxidizing gas in there, which is oxygen. And it makes this solid calcium sulfate, which turns into a solid and sinks to the bottom down here. And I guess you could have like a little container or like a hatch and you could scoop it out as it's being generated. Calcium sulfate is actually a valuable product in its own right. It's used in drywall. It's that white powdery stuff that you find inside a drywall, also called gypsum. It's a mineral that's mined. There used to be big gypsum mines, I think, in Digby. And I think the railroad that goes through Wolfville used to carry the gypsum, but I think that has like been dramatically reduced since the installation of scrubbers, because now there's a cheaper source of gypsum that actually produces gypsum that's more pure than stuff you can mine anyway. So this is great. It takes the SO2 out of the air. Not only that, but it turns it into a valuable product that you can then use to build drywall, put it in houses and things like that. I learned yesterday, actually, calcium sulfate you can also buy as something to add to your garden. It's apparently amazing if you have clay in your soil at making it more, at breaking it up. It's better than sand, it's better than organic material. So there we go, a couple of uses for this thing. Now, what makes scrubbers a good technology or a successful technology within a short period of, maybe 10, 20 years, fixing this problem kind of at once, is you just need to put one at each power plant. It's not like every single vehicle, every car needs one of these. You just need one per power plant. And, a province the size of Nova Scotia has, I don't know, maybe 10 power plants that burn coal. So installing these isn't really, an unrealistic or difficult thing to do. Where if you had to put a scrubber on every single vehicle, that's obviously a bit of a different story. But vehicles, generally speaking, don't produce SO2 because the fuel they burn, gasoline, doesn't contain sulfur. SO2 emissions, sure, we fixed the problem in North America and in Europe, but it's still a problem in other parts of the world, certainly in China and India. And my numbers here are kind of older. They're 10 years old already. I'll try to get maybe some newer ones there. But certainly areas that are experiencing huge amounts of growth in their industrial sectors hopefully can basically avoid the worst of the issues that we saw here because the technology already exists. So really what they just need is regulation present in these countries to put this in. Why don't they just put them in anyway? Well, it's expensive to run these. It costs money to install them, to operate them. And so therefore, it lowers profits. So unless the government tells you have to put this on, or makes it expensive to not have them, then industry just won't do it. And you can blame industry, but if they're being very environmentally conscious and no one else is, well, the other people will have a competitive advantage and then you're not going to be in business much longer. The issue of sulfur dioxide production in North America has been largely addressed using scrubber technology. Chemically speaking, what do scrubbers do? They clean the inside of the stack where SO2 is generated. They react SO2 with water to make sulfuric acid. They convert the SO2 to CO2, or they react SO2 with calcium hydroxide to make calcium sulfate, also known as gypsum. The answer is D. It's the last one here. All right, 316. So we're doing pretty good. We're going to look at another gas now. So we've checked off 2, carbon monoxide, SO2 gas. The next gas, which is another important pollutant, and this is produced by cars, is NO2 gas. And this reaction that you see in the video is the reaction that's shown up top. It's copper metal reacting with nitric acid. What's in here is nitric acid, HNO3. And if you throw in copper, like a copper penny, this reaction will start. It'll produce copper nitrate, which is sort of greenish blue. Look at the color of the water. It looks kind of green. That's copper nitrate being formed. And the NO2 gas is being generated. And you can see it spilling out, right? It's coming out of here. And it's orange. It's bright orange. And it's very obvious. It's formed in a number of other ways too. It's not just formed by mixing copper with nitric acid. It's formed also whenever you burn something at a high temperature and typically high pressure when there's nitrogen present. So really, anytime in your car engine, when there's high pressure and temperature, which is like the explosion inside the piston, there's oxygen and there's nitrogen because there's air in there, they can combine and form some NO2 gas. Collectively, actually, we call these NOx gases because you can also have NO, NO2, NO3. There's some other forms. You can have like N2O. Collectively, they're called NOx gases, although NO2 is the primary one that we worry about. Great. So whenever you heat oxygen and nitrogen together, especially if they're under pressure, you get some NO2 gas. So your car, as it's running, is constantly at least producing some. The amount depends on the temperature of the explosion in the engine. It depends on the pressure, depends on a few other things as well. Depends on the gas mixture. But what we do know is that diesel engines typically produce more NO2 than gas-burning engines. And since many of our vehicles out there are burning diesel, this is an issue. NOx, it can contribute to acid rain. It can turn into nitric acid and come down as acid rain. But that's actually not its biggest problem. Biggest problem is that it gets in the air. You can actually see it in the air in some cities. It gets hazy and orange looking, the air. And when it absorbs sunlight, it can create what's called ozone, ground level ozone, which is very damaging to our lungs. It's a big problem if you have respiratory problems, if you have, COPD or asthma or, cystic fibrosis or anything where your lungs aren't operating at full capacity. You can be very sensitive to that. So here's a picture of Santiago in Chile, which at least at one point was believed to be one of the most polluted cities in the world in terms of its air quality. And when pollution was bad, when the pollution index was high, this is what the city looks like here on the right. When it was very low, it would look like it does on the left. And this city sort of has the perfect storm of factors which cause it to have this high pollution. One is many people living in a small area, dense area, driving cars, producing a lot of this stuff. And it's also nestled up against this mountain range that you can see in the background, which at certain times of year prevents air currents from carrying the polluted air away. So it kind of will sit there and then get worse and worse and worse and worse. And we have a name for this. We call this smog. And you can kind of look, in this picture, it looks a little bit orange. Is that orange kind of tint or hue? And that orange is from this NO2 gas. So smog is the actual term for when you have so much of this pollution that you shouldn't be going outside. We're lucky right now to be in Wolfville, at least those of us that are currently in Wolfville, because as long as I've ever been here, as long as I've ever lived in Nova Scotia, I've never heard of there being a smog warning. But in big cities, in Canada even, in Ottawa, when I lived there, we would get smog warnings sometimes in the summer. And in other cities, it's very, very commonplace. And the idea is if you have respiratory issues, don't go outside when there's smog warnings taking place. Toronto will get smog warnings. This is Toronto on a smoggy day on the right versus the same picture on a clear day. Hopeful, though, we're pretty lucky. We don't get smog here. We don't have enough population density. We don't have enough cars. Don't have enough traffic for this to ever build up to an amount which will pose a health risk, which is fantastic. We have very clean air. You may remember a few years ago, there was a big scandal that involved Volkswagen. And what they were doing is they had programmed computers inside the car to detect when these cars were being driven normally or when they were undergoing emissions testing. So somehow the program knew, and it would operate differently under testing scenarios to meet certain emissions targets. And then when you go out and drive on the road, it would just turn off that mode and go back to its normal polluting mode. So it was allowing it to cheat emissions testing. And this is saying there was nearly 1 million tons of extra pollution that these cars produced over the period of time that the scandal was running. And the gas that they were worried about that these cars were producing was NO2. And it was diesel engines that were doing this. My father owned one of these vehicles, and they had actually a very generous buyback program. I think he had the car for maybe 4 years or something, and then they just bought it back for his purchase price. It's pretty sweet. These are the NO2 levels on the planet from 2009. You can find these numbers, they vary certainly year to year, but what you can see is that where the worst areas are on the planet corresponds to where there's high concentrations of population. Right? So you can see, and not just population, but industrialization maybe is another way to say that as well. So not just people living there, but people who are driving cars, who are operating factories, all these sorts of activities that would produce NO2 gas. So yeah, Eastern Seaboard, US, Europe, much of China. So lots of different parts of the world that produce this. Now, there have been gains. Since the 90s, we have reduced the amount of NO2 that is being produced by vehicles. Whether this, so I'll say this. It's not the same success story as it has been for SO2. SO2, we got rid of like 90+% of it. We're down to levels of SO2 where really the problem of acid rain has gone away. With NO2, the problem of smog has not gone away. We've reduced it. It's not as bad as it used to be. It's better now than at any point in my life, certainly. And this has largely come in as the result of legislation around emissions for vehicles and industrial equipment and stuff like this. If you buy a new car, it's going to produce less NO2 gas for burning the same amount of fuel than a car from the 1970s would. And we're making progress on this. Certainly, I think the coming revolution will be when electric cars replace gas-powered cars just wholesale. A lot of you may have children that will never have heard of a gas car. Might be maybe a stretch, but certainly I think in like 20 or 30 years, predominantly electric cars, this should hopefully go down to zero. Vehicles are the main source. All right, what pollutant is an orange gas and primarily responsible for smog? CO2, CO, NO2, SO2. So we know the answer is NO2. For the people online, is my audio still messed up? And I'll wait 15 seconds and get that answer. Modern gas-powered cars produce much less air pollution than older ones due to the addition of what feature? Power steering, Bluetooth, catalytic converters, cruise control. Yeah. I see a lot of yeses in the chat, and I forget what I asked. Is it better, or is it just as bad as before? We'll see. I don't know. Okay. People are getting used to it. Maybe they like my robot voice. Yeah, the answer is catalytic converters. I've heard that cruise control actually burns a little more. No, maybe cruise control. I think maybe I'd save you a little gas because it prevents you from accelerating too quick, or I don't know. Did I asked if it was bad? People are still saying yes, it's bad. Okay, thank you. I don't know what to do about it at this point. Nothing. All right. All right, so the next thing I want to talk about is smoking. Why is smoking bad for you? Why is breathing smoke from any source bad for you? Remember back, one of our first units, we talked about the different categories of carcinogens, group 1A and 2A, probable carcinogens and all this sort of stuff. One of the ones that's in the second class, which is probable carcinogen, is sitting by a campfire. And the reason why sitting by a campfire can increase your risk of getting cancer is due to compounds that are coming off of the fire that you're breathing in. And it's the same thing that you get from cigarettes or smoking anything, or being exposed to any other sort of like fine particulate dust that could be present in the air. Smoking contains 4,800 different chemicals, 400 toxic, 40 carcinogenic. Which sounds bad, but that's meaningless, remember? If we don't know the doses. Yeah, an apple probably has 400 compounds, and what does even toxic mean? How toxic? Carcinogenic, well, how much of them are there? Is there enough to cause a difference? We actually know the answer to that too. Obviously, smoking's bad for you, bad for your health. Rush Limbaugh died this week of lung cancer after stating on his show 6 years ago that he didn't believe that smoking caused lung cancer. And he was an avid cigar smoker, so what you get when you ignore things, I guess. Opinions towards smoking have changed a lot. Maybe not so much in my lifetime, but maybe a little older than that. This is an ad saying more doctors smoke Camels than any other cigarette, which is, of course, trying to implant the idea in people's minds that doctors, who, of course, are concerned with health, smoke, so how bad can it be? This one I found very interesting. It says, blow in her face and she'll follow you anywhere. And I don't know when this is from. This is an old commercial, obviously, but I don't know. Like, I think blowing smoke in someone's face is an insult, right? So, anyway, this is just puzzling to me why someone would believe that. This is another one. Melissa Williamson worries about the effect on her unborn child from the sound of jackhammers as she smokes a cigarette, right? She should be worried about the cigarette that she's smoking, not the sound of jackhammers. What makes smoking bad for us? And smoking anything, it doesn't have to be tobacco. It could be marijuana, it could be anything, is the fact that it produces smoke. And smoke, it's not the THC I'm talking about, it's not the nicotine I'm talking about, it's the little black particles of soot. These are particles which are generally insoluble, they do not dissolve in water, and we breathe them into our lungs. And our lungs have these little structures called alveoli, which, you know, you can think of your lungs being out here, they're like little pockets. And you can see here this little capillary that runs along the outside of this. And the idea is oxygen enters in. It can be absorbed into the bloodstream. CO2 can come back out. What these basically do, these little structures, these alveoli, is they provide a greater surface area inside your lung for oxygen to interact with your membrane and exchange back and forth, and to rid yourself of CO2 as well. So it allows your effective surface area inside your lungs to be much larger than your actual size of your lungs. What can happen is if you have particles that are insoluble in water, that are around 2.5 microns in size. So 1 micron, which has that symbol, is 10 to the minus 6 meters, which is 10 to the minus 3 millimeters. So basically 1,000th of a millimeter in size is 1 micron. So if you have 2.5 of these in size, they're kind of just the right size of this little particle here to kind of wedge themselves into these little alveoli and block the rest of it in there, block air from getting in and out. So what this does is it basically reduces, when these get clogged up, it reduces your lungs' ability to exchange air in and out. So it reduces your lung capacity, it reduces your lung function. And you probably have seen pictures like this before of a healthy lung and a smoker's lung. Well, I say it's a healthy lung, but I think whoever owned that lung is not very healthy right now. But anyway, if you are healthy, that's what your lung might look like on the inside. Smokers' lungs turn black, and that's because of the soot that builds up inside the alveoli. Enough of that black material will build up over time and block enough of these that you can see it. The lung looks physically black. So of course, that makes it harder for your heart, because your heart has to pump more blood through faster, higher blood pressure, higher heart rate, in order to make use of the lower surface area that you have in your lungs. It causes irritation, it can lead to lung cancer and all these sorts of things too. By and large, many of the negative aspects of smoking have nothing to do with the nicotine. It's to do with these particles that you're breathing in all the time. And cigarettes are filtered, but those filters are not sufficient to filter out these very, very small particles. They don't do the job. Vaping is an alternative, and vaping, I think we're probably yet to see the problems associated with vaping. I think it's maybe newer, and we don't have the data we have for smoking yet. At least it shouldn't have this particulate matter. The thinking is with vaping is that it should be safer because you won't have this. But there may be other problems associated with it that we don't understand well yet. Of course, not inhaling anything that you don't need to inhale is the best idea. You can get PM 2.5. This PM 2.5 is just particulate matter, 2.5 microns. You can get it from other places besides smoking. And this guy, this is not blackface. This is not him being insensitive. What he's doing is he came out of a coal mine, and he's been exposed to coal dust that has basically covered his face with basically covered all his exposed skin. And of course, he's wearing a shirt, so down there he didn't get any on his skin. And he's in the bath washing himself off. And notice he's also smoking. So he's doubling his source. And if you see what his skin, his hair, and everything look like, the inside of his lungs are likely to look like that too, because he's breathing that in. In fact, his lungs probably have more exposure to this because they're constantly breathing it in and breathing it out. So coal miners, this is very common. They have what's called black lung, the disease of coal miners, constantly breathing in coal dust in a coal mine without proper filters or anything like that. Same effects as smoking. You can get particulate matter also from things like volcanoes. Produce a lot of soot, and it's just ash. It can fly everywhere, and it can be very high in particulate matter. You can see these vehicles are covered in this ash. Forest fires produce a lot of particulate matter as well. We get that every once in a while. Every couple of years, there'll be forest fires in like Quebec, and the smoke will blow over in Nova Scotia, and we can actually kind of see the air gets a bit hazy. But this is something else you don't want to be breathing in, same as cigarette smoke. If you sit by a campfire, same thing. And the World Trade Centers, when those collapsed, that produced a lot of very fine dust as well. And that, of course, you had people breathing that stuff in too, which caused a lot of respiratory illness there as well in the city. Question, what does PM 2.5 mean? 2.5 picometers, particulate matter 2.5 microns, pulmonary material 2.5 microns, particulate matter 2.5 meters. Correct answer is B, particulate matter 2.5 microns in size. I was told that last ad, Blowing Smoke, was from 1969, which is what, 30, 40, 52 years ago? Quite a while. But not that long when you think about it. Why is PM 2.5 a health concern? It causes stomach cancer. It obstructs alveoli in the lungs, negatively affecting respiration. It damages the skin and can cause skin cancer over the long term. It can easily cause a toxic overdose. The answer is B. All right, so this is showing pictures in Canada where particulate matter levels. So this is measured across the country. And you can see the different levels there. Red means, relatively high. The pale yellow is relatively low. You can see in Nova Scotia, we're sort of generally in the low to moderate area, except for Halifax. In Ontario and Quebec, it's sort of this corridor here that is heavily populated. Again, you see like Edmonton, Calgary, Winnipeg. I mean, there's not a lot of people in Regina, but a little bit elevated levels in Regina, Vancouver, and Victoria. Basically, where the centers of population, you have higher amounts of particulate matter. You have more human activity. You have more people burning wood in their fireplace and going up the chimney, which produces smoke. All these different sources that produce particulate matter increases with human population. And it's super low, right, in all these northern areas where population is very, very sparse. Particulate matter levels have been dropping the last couple of decades, basically due to replacing more polluting technologies with ones that pollute less. But I'm going to show you this map, and this is maybe the important one. This shows you the PM 2.5 levels on a world scale. And you can see here, these are the very high levels towards the red. Blue is very low. And essentially everywhere in Canada is low. So, there are some hot spots where it's a little bit higher than other parts of the country. But generally speaking, PM 2.5 isn't really a big problem in Canada. Especially in Nova Scotia. We're in a pretty good place. We have very clean air. Very clean air according to SO2, according to NO2, according to PM 2.5, and now carbon monoxide as well, the catalytic converters. So if you want clean air, you're in basically the best place in the world. So notice, certainly in parts of Asia, but notice up here, there's very elevated levels. Northern Africa, Saudi Arabia, Middle East, which might surprise you initially because there's not a high population there. Not a lot of people. There's not a lot of industry there. There's not a lot of cars. There's not a lot of factories. What is there, do you think, that could cause all this particulate matter? Yeah, the desert there. Sahara Desert, which is sand, and wind will blow the sand around and grind it down into small particles, and those particles will eventually reach PM 2.5 size. So there's huge levels in desert areas just because of the wind blowing the sand. So sand, it'll do the same thing if you breathe it in. I believe black lung is if it's carbon-based. I believe they call it silicosis. You breathe in sand. Because silica is chemical name for sand. How much we got left here? I feel like I got just a couple of slides. I'm gonna quit her now. I think we're good. We'll finish this easily next class. We'll start the next unit shortly after. But I'm gonna call it quits here, and I'll see if I can figure out why I'm sounding like a robot today. But yeah, sorry for everyone that had to put up with that for the last hour and a bit. Great weekend, everybody. And it'll be a week from Tuesday that the unit quiz for this unit will be due. Thanks very much, everyone. See ya.